Okay, so we want to talk about even and odd functions. And the first thing to realize is that most functions are neither. This is just a special case. Like these are two special cases. Certain functions have these properties. We like to know when they're even or odd because it makes graphing them really easy. Like you have to do actually half the work. For every point you find, you get a free point. Like a buy one, get one free function. So what this means here is if a function is even, this is on your paper there, but you can probably want to make some notes, can be reflected onto itself over the y-axis. Right, so you can take it, every point in the first quadrant will reflect onto the second quadrant. Right? Every point in the fourth quadrant will reflect into the third quadrant. So think about all the reflection stuff that you did in geometry, right? This is an algebraic kind of version of that. Now, what that means in terms of its algebraic definition is f is even if f of negative x is equal to f of x for all x in the domain of f. Don't worry about this bottom part too much. It just means that you can never prove anything odd or even by saying, here, look, I checked 5 points and they work. You got to check all the points. And for a function, that's not feasible because there's an infinite number of points. So we have to use algebra here. Okay. So as you guys guessed already, even functions tend to have even powers, just kind of in general. So if we look at this first one, we have on the worksheet here, for example 1, we have f of x equals x squared. This is the most even function ever. Like this has all the properties that we want, and it's kind of easy to see because it's actually to the second power. But if I go ahead, if we graph this, here's what it means to be even. Is if we're graphing this function, and we're making a table. Now we'll confirm it's even here in a second. But when I make the table here, or the xy table, I'm going to put in 0 and I get 0. Now you can't reflect that point across the y-axis because it's on the y-axis. But if you put in 1 here, I'm going to get 1. Right? Because it's even, it says that if I put in the opposite of 1, I'll get the same answer as I did with 1. So this point shows me that then negative 1, 1 is also a point. That's what it means to be even. So if I put in 2 for this function, I get a 4. What other point do I know then?
Negative 2.
And
4.
Yeah, that's all. That's what it means to be even. So if you recognize that you have an even function, you only have to find half as many points to graph it. It's kind of the advantage. So here we can finish our graph, which is not super important here in terms of this problem. So how are we going to prove it is what we have to do here. So to verify, this is the algebra part. This is the part where the process is important. The answer is really not that important. It's the process. Can you show that I started with this, I applied these things, and then I get this result? So for this one, I would say, just go ahead and write your function. And then what we're going to do is we're going to evaluate f of negative x. So you're going to take the rule for f that we have, which says take the function and square it, or take the input and square it, and we're going to evaluate f of negative x. So we're going to take negative x and square it. Seems reasonable, right? So when you square a negative number, we know that we get a positive, don't we? So if I do negative x times negative x, I just get x squared. So now we have f of negative x is equal to x squared. And here, notice that this is f of x, right? F of x we started with was x squared, right? So I'm going to take this x squared out, and I'm going to replace it with f of x. So then we get f of negative x equals f of x. which was our definition of even, and we say therefore f of x is an even function. That's pretty much the process. Okay. All right. So here we have f of x equals x cubed. You might guess that's an odd function. What makes it an odd function is each point can be reflected onto, well, the function can be reflected onto itself through the origin, right? So if you have a point in the first quadrant, it'll reflect to the third quadrant. If you have a point in the second quadrant or fourth quadrant, it'll reflect to the second quadrant. So what that means is, as we look at this, is that if you plug in the opposite of x into the function, you'll get the same output as if you would have put x in and just made it the opposite. It's not quite as nice as that evens, but if we look at a table here, f of x equals x cubed is an odd function. We'll verify it in a minute. But if I look, now 0, 0 is just a point. You can't reflect it through the origin because it is the origin. But if I put a 1 in here, I get 1. If I put negative 1 in, I get the opposite of 1. If I put in 2, I get 8. Negative 2, the opposite of 8. Again, you're getting a free point every time. If it's an odd function, right? So with evens, we made the x the opposite and left y the same. For odds, you make x and y both the opposites. Okay. Again, most functions are neither even nor odd. So if this doesn't work, it just means it's not even or odd. It's a nice thing to find if it does happen. So to verify, we're still going to go back and do pretty much what we did with an even function. Just have one little piece at the end we have to add on. So let's verify that f of x equals x cubed is odd. And to verify means show work and do algebra and stuff, not just say, yep, it is, or, check, true. So here's the function. I'm going to find f of negative x. So I'm going to take the function. Everywhere there's an x, we're going to replace it with negative x. So that gives us negative x cubed. And the reason we're using x's here is because we're proving it for every x in the domain. Now, when you cube a negative, does it stay negative?
Yeah.
Sure. So we get f of negative x equals negative x cubed. Okay, so we plugged in the negative x, we evaluate. And then this next step, we're really looking to substitute. Now, this is different up here, correct? But it's the opposite, isn't it? So we just say this is equal to the opposite of f of x. So we did some substitution. So therefore, f of x, which is equal to x cubed, is an odd function. So that's what you have to do. You just, again, you substitute in, you put in negative x, right? Simplify it. Then hopefully you can pull out the x cubed and replace it with f of x, but we got f of negative x equals negative f of x. That's the definition of odd, right? The definition of even was that the negative just disappears. The definition of odd is that you can pull the negative outside. For instance, when we get to trigonometry a lot, the sines, cosines, tangents, all that stuff, they're even and odd. Like if you know they're even or odd, that's good. Okay, so 3 examples here from the back of the worksheet. We have h of x equals 1 minus x to the 4th. So that's the original function. To determine if it's even or odd, I have to do h of negative x. So I'm going to put a little squiggly here to remind myself that I have a new function. But h of negative x would be 1 minus negative x to the 4th. All right, just pull this x out, replace it with negative x. This is super important to show your work because people tend to miss these because they have trouble with negative signs, right? And this is like a great place to have trouble with negative signs because they're everywhere. So you really have to be careful and keep an eye out. And notice here, I pulled out the x and I replaced it with a negative x in parentheses. I did not say, oh, minus a negative, I can make that a plus, because you know that's wrong, right? Because this is to the fourth power. So be very careful there. So our next step is to simplify. Well, 1 is just 1. And then that's still minus. What's a negative x raised to the fourth power? Would the negative go away? It would just be x to the fourth, right? What does that look like? The original function, right? So h of negative x is equal to h of x. Therefore, h of x is even. Right? That's the definition of even right there. That basically that negative input on the x just goes away. You get the original function back. Now, you could tell this also, a constant is considered degree 0, but 0 is an even number also. So every power is even. Now, you could get these a little bit kind of more complicated with trig functions and some rational stuff, but we don't need to really do that. So this next one is g of x equals 2x minus x squared. So I'm thinking here it's going to be neither, right? Because we have an even and an odd. Let's take a look. G of negative x is 2 times negative x minus x squared. So from this, we get negative 2x. Negative x, when I square it, just becomes x squared, doesn't it? Or you could think there's like 3 negatives, if that helps you. But however, you get minus x squared. Now, does that match the original? Yeah, that's 2x minus x squared. There's a negative there, so it doesn't match. If it doesn't match, which we'll see a lot, try to factor out a negative 1. Okay, so at this point, if it's not even, which it's not because it didn't match, factor out a negative 1. So my next step here would be negative and then 2x plus x squared. But if we look, does that match the original piece? No. So if it didn't match here, and if you take a negative 1 out and it doesn't match, is it ever going to match? No. No. So it doesn't, so this is neither even nor odd. Or just put neither if you wanted to, whatever you want to do.
Can I say Evod?
No, because that's just weird. No. But we'll just say even or odd. All right. So let's look at this last one here. So we have f of negative x is negative x to the 5th plus negative x. Right? Again, every x gets replaced with negative x. And then we get negative x to the 5th minus x. So I've simplified it. Does it match? So if once you simplified it, if it doesn't match, the only thing left is to try to factor out a negative 1. So when we do that, negative x to the 5th plus x, does that match the original? Well, except for the negative, but I mean this part matches, right? So we could say f of negative x equals negative f of x, which is the definition of odd. Yeah. So therefore, f of x is odd, meaning that it's going to have the reflection symmetry through the origin. So there you go.